All right, we're going to look at logarithmic functions. So if we start with an exponential function, and remember that to be one-to-one, and to make sure that then we can have an inverse of our function, we don't want to have something like that, because that would just be a horizontal line at y equals 1. So we don't want that. So we make sure that a is not equal to 1, and we also want to make sure that this is positive so that we have a continuous function. Okay, so what happens is if we're going to try and figure out how to basically kind of undo how to get up into that exponent position, we need to introduce a new function, which is called the logarithmic function. Okay, now this is just a straight definition, okay? To get at that y, to solve for y, we're going to introduce this idea of something called a logarithm, okay? So the way that this works is we have our base. That's the base of the exponent problem, okay? And so it would be the same base of the logarithm. And then we have the answer to the exponent. That's in a logarithm, that's called the argument. Okay, and then that would be equal to y, which is the exponent. Okay, so let me just show some examples here. So if I have this function f, f of x is equal to 2 to the x. Okay, so I'm going to graph that. So when x is 1, we would be up at 2. When x is 2, we'd be at 4. When x is negative 1, we'd be at 1/2. Okay, so there's our function f. All right, and now if we look at its inverse, okay, so the inverse takes and just switches our x and our y. So if we had an input of 1/4, would come a -2. Okay, so when you take log base 2 of 1/4, the answer to that is -2. Okay, and we can always understand that by just using the actual definition of what it means to be a logarithm. Okay, so logarithm means that's equivalent to the base of 2 okay, we're still going to have that same base, but that's going to be in our, that's the base of our exponent. Okay, that to the power of -2 is indeed 1/4. Okay, and let's think about what it means to have log base 2 of 1/2. 2 to what power is equal to 1/2? It's the -1 power. Okay, so that would be our exponent. And that is the answer to the logarithm. 2 to what power is equal to 1/2? It's -1. Whoops, that should be a negative. -1. All right, let's try this next one. Okay, input is 1, and it looks like this. Log base 2 of 1. And what this means, 2 to what power is equal to 1? Okay, so we're always looking, for the answer. 2 to what power? 2, sorry, that's our base. That should be in. 2 to what power is equal to 1? The 0 power, right? Okay, so out goes. Okay, this next one. We go and input a 2, 2 to what power is equal to 2? That would be 1. Okay, so the answer to that is the exponent there. 2 to what power is equal to 2? Okay, so we're always thinking the base to what power is equal to the argument. Okay, so the base to what power is equal to the argument? The base to what power is equal to the argument? Now, when we go to graph this, we're going to get this nice function. It's now not going to have a y-intercept. It's going to have an x-intercept at 0, 1. And it's going to have now, let's see, at 2, that was 1. And at 4, right, log base 2 of 4. So that means 2 to what power is equal to 4? And that should be a 2. Right, 2 to what power is equal to 4? That power is 2. Okay, so when we go to graph all of these, now we're going to have 4, we're going to be up at 2. At 2, we're at 1. At 1, we're at 0. At 1/2, we're down at -1. At 1/4, we're down at 1/4. So it's that mirror image that we get when we have inverse functions. And so now with a exponential, our domain went from -infinity to infinity with a range going from 0 to infinity. The x-intercept, there was none. The y-intercept was 1, 0. Horizontal asymptote is 0, y equals 0, and there's no vertical intercept. Okay, but now for our inverse function, now we've got a range going from 0 to infinity, or sorry, a domain, and our range is all possible y values. Our x-intercept, now we do have an x-intercept at 1, 0, but we do not have a y-intercept. We have no horizontal asymptote, but we have a vertical asymptote at x equals 0. All right, so that's the inverse. That's kind of how you undo exponents and get up at the variable in the exponent position. Okay, so a logarithm is the inverse of an exponential. All right, let's look at transformation. So here's our parent function, f of x, and I'm using log base 2 of x. Okay, so let's look at this first transformation. If we have y equals 2 plus log base 2 of x, as we can expect when we're adding 2 to the output, that's going to be a vertical shift, so everything shifts up 2 units. Let's see, we'll do this one. All right, and then this would come right up. So we still have that same vertical asymptote. We're just shifted up. So our domain is going to be the same. Our range is going to be the same. Vertical asymptote is the same. Now the y-intercept, that's coming from this point. No, it's kind of a mess over here. Let me erase some of that. Okay, so let's see what happened. This was at 1/2, -1. This point is at 1/4, -2. So if we shift up, this point right in here is that y-intercept is at, or sorry, I'm saying the y, but the x-intercept is at 1/4 and 0. And then it does not have a y-intercept. Okay, that's coming there. Good. All right, so now let's look at this next one when we're adding 2 inside the argument, and that is going to be our vertical or our horizontal shift. Okay, so we've got our original, and we're just going to shift everything to the left. I'll do this in green. Okay, so this was over at 1/4 -2. So it's going to come over at let's see, a little bit, 1/4 away from -2 there. And then we've got here 1/2, and then this one, 1, 2 is here. 1, 2 is here, so we will have a y-intercept. This one goes back 1, 2, and it's going to affect our vertical. Okay, so that was number 2, y equals log base 2. Okay, so when we go in and add 2 inside into the input, that's the horizontal shift. Okay, so here we have our domain has switched and scooted back to -2 to infinity. Our range is still everything. Okay, and now our vertical asymptote is now right here because it's originally the parent graph has that horizontal or vertical asymptote at x equals 0. So now we're at x equals -2. We do have a y-intercept at 0, 1, and we have an x-intercept as well at -1, 0. Okay, so let's see what we think might happen for the third one when we have y equals the opposite of our parent function, log base 2 of x. Okay, so this is where we have our reflection about the x-axis. So all of these are just reflected here about the x-axis. So that's the third one. All right, and let's just see what happens there. Our domain is going to be the same as the parent, as is our range. Our vertical asymptote stays the same. We don't have a y-intercept, and our x-intercept is the same. Okay, but now it's a decreasing function. All right, and the last one is where we do the opposite of our input. Log base 2 of the opposite of x. And that's the one where it's going to be a reflection about the y-axis. So we're here instead of this nice y-intercept or x-intercept at 1, 0, now we're reflected, we're back here. And then this point here will be reflected across, as will this one. 1, 2, 3, 4. Okay. So we still have that same vertical asymptote, but now let's see, our domain is going to go from -infinity to 0. Our range is the same, -infinity to infinity. Our vertical asymptote is the same, but our y-intercept now is, oh, we still have none, right? Okay, but it was the x-intercept. That's the one that switches to -1, 0. Okay, so now let's look at some of our most common bases. We have a base 10 and a base of e. And so if we have a base of 10, it's just not even written. There's no base written at all. Okay, so these are equivalent. And then if there's a base of e, here we would just, we actually just call that the natural log with that e, because that base of e is really how things grow in nature. Okay, so those are really common, and most calculators really will only compute those logarithms. All right, so now we're going to use this natural log, and so that what that tells me is it's got a base of e. So let's look and see what happens with all these transformations, and we'll use our parent graph of y equals the natural log of x. Okay, so we have our classic x-intercept there. And then we have when we're trying to graph logarithms, the easiest thing to do is to rewrite this in terms of exponent form. Remember that ln, that means base of x, okay? Or sorry, base of e. And then we just use the definition of logarithms. We have the base of e to the power of y e to the y is equal to the argument, that x. Okay, and then we can just plug in some different y values here, 1 and 2. Okay, and so I just did this one, e to the 0, that's a 1. Let's do e to the negative 1. That would be 1 over e. E to the negative 2, 1 over e squared. E to the 1. And e squared. Okay, so now we can graph our parent function. So when y is, let's see, when y is 1, we're at e, and e is about 2.7. When y is 2, we're at e squared. And that's about 7.4. So when y is 2, we're kind of off the graph over at 7.4. Okay, so this is that point at E1. All right, so now let's look at some of the transformations. So the first thing I'm going to do is I'm going to look at reflecting about the y-axis. Okay, so let's do that. We're going to reflect over. So now we're at here. Okay, that was number 1. Equals ln of opposite of x. Okay, now let's look at the second transformation, and we will have reflect about the x-axis. Right, that would be the opposite of our function. Okay, so I'm going to do that. Let's see, I still have this, but now this one is coming here. Okay, great, so then we've got that reflection about the x-axis with this opposite of right here. All right, and then finally, we're going to do a vertical shift. So y equals 1. So we're adding 1 to all of that. So everything's going to slide up 1 unit. So up we come, and there's our final graph. And now we can figure out the domain. Domain of f. Let's see, that would go from -infinity to 0, and our range is going from -infinity to infinity. And I just want to label that horizontal asymptote at x equals 0. And this one is our f right here. All right, so now let's look at just the domain for our logarithms. Our argument is going to be positive because remember we've got a to what power is equal to the argument, and our base is in an exponential function, our base is positive and not equal to 1. So we have a positive number taken to a power. If you had any positive number, like, I don't know, say 4, and you take that to the any power, that's 1. You could take it to the -1. 4 to the -1, that's still positive. How about 4 to the 1/2? Okay, always what's coming out of an exponential is a positive number, and for logarithms, the argument is this answer to the exponential functions, right? This is the argument. All right, so anyway, the argument of a logarithm is always positive, and so if you're trying to find the domain, we would just take the argument, and then we can set that x squared minus 4 is greater than 0. And then we're going to solve that. Let's see, we would do factor it. And then we're just going to figure out our key points. X equals 2 and -2, and then we want to figure out, using a sign chart, what our signs are here, -2 and x plus 2, and then we really want to know what our function is. All right, so let's do our test points. Let's say -3, how about 0, and maybe +3. Okay, and so -3 minus 3, that's negative. 0 minus, or -3 minus 2, that's negative. 0 minus 2, that's negative. 3 minus 2, that's positive. And when we put a -3 plus 2, that's negative. 0 plus 2, 3 plus 2. And then our function here, negative times negative is positive. Negative times positive is negative and positive. But our question was right here, when is this greater than 0? So we were looking for that positive. So it's right here and here on our graph. So it's along here. We don't want it to be equal, so we're going to use parentheses there. So the domain of f would be from -infinity up until that key point of -2, and then we jump over to 2 and head off towards infinity. Okay, let's try this next one. There's two things going on. We have a square root and we also have a logarithm. So we're going to use those two things working together. Okay, so with a logarithm, the argument needs to be positive, and also when you're taking a square root, you need to be taking the square root of something positive. So we'd set the radicand greater than or equal to 0, and subtracting 7 from both sides here, and then dividing through by -1. Got to change the direction, but you got to flip because we're dividing by a negative. So it would be x is less than 7. Okay, that's our first bit of information, and then here we have x minus 2 is greater than or equal to 0. Adding 2 to both sides, we'd have x is greater than or equal to 2. And you put both of those together, so we have at 2, your 2 or greater, and at 7, you can't be 7, but you're anything smaller. So our domain here of h is from 2 inclusive to 7, and don't include that. All right, now let's look at our properties of logarithms. So these are really based on what it means to be a logarithm. So this first one, a to what power is equal to the argument? Well, it has to be 0. Right, there it has to be 0. Okay, let's look at this next one. The base to what power is equal to the argument? Well, it can only be 1. Okay, let's look at this one. The base to what power is equal to the argument? That it has to be an x there. Okay, so these properties really, it's just about really understanding what it means to be a logarithm and what that definition means. Okay, here now I have something in an exponent form. So I'm going to take that base of a, and I'm going to say log base a. Okay, let's say that I didn't know what this was. That's just a big question mark for me. Okay, using the definition of how we work from an exponent and put it back into logarithm form. You take the base of a, so it's log base a of what is equal to the exponent? Log base a of x. Well, in order for that to actually be a true equation, then the argument must be x. And then here's the same properties with the natural logs. All right, so using those, let's see, this has got to be 4, and that's by property number 3. But if you don't have these properties memorized, you can always just figure them out. Okay, so let's say that I didn't have that memorized. Okay, I'm thinking the base of 5 to what power is equal to the argument? That has to be a 4. All right, let's look at this one. 4 to what power is equal to 64? Let's see, 4 squared is 16. 4 cubed is 64. So this has to be 3. All right, let's look at this one. This one, I usually put that base of 10 in there just to help myself, and 1/10. I would say that fraction out loud as 1/10, so I'll just write it as a fraction. Or I would say the decimal that worth is worth 1/10. Okay, and then this would be 1/10 is the same thing as 10 to the negative 1. All right, and then this is based on property 3. That is negative 1. Okay, log base e, when you see that ln, let's see, and this is this cube root of e, that means the same thing as e to the 1/3. Okay, so then that is equal to 1/3. Okay, now we're going to solve equations. We just really need to be careful and just double check, make sure that your answers work. All right, using what I know about exponents. This is log. It doesn't have a base, so we know it's a 10. So this means 10 squared is equal to the argument. 100 is equal to x minus 4. Add 4 to both sides. X is equal to 104. And then we'll just quick double check. Just make sure. Log of 104 minus 4. That would be log of 100. And log of 100 is 10 squared. So that is equal to 2. Okay, let's try this next one. Okay, I'm just going to rewrite this in exponent form. X to the second power is equal to 100. What squared is 100? Well, it's either, if I was solving this, I would do positive and negative square root. But positive 10, right, or negative 10. But when I go to check, log base 10 of 100 is equal to 2. That works, right? 10 squared is equal to 100. So that one works. But if we tried to have log base negative 10 of 100 equals 2, that does not work because that is not in the domain of logarithms. The base is positive and it's not 1. Okay, so that one does not work. So we only have one solution there.